Hello and welcome everyone to the first devlog of a series for a project I've been working on for quite a while. The work name of the project is Irregular Engine, and as you can see, it is a rendering engine. In fact, I've been working on that for over a year now, but I decided to now start with a little devlog series. I don't know how often I can make these videos or how many people are actually gonna watch this, but even if no one does, I just make them for myself. So I prepared a few things to show. The very first thing is this sphere thingy here. In fact, this is actually not a sphere, but is a cube. It is a cube rendered with a special set of textures to enable it to actually look like a sphere. The technique is called parallax occlusion mapping and is the same technique that is used to generate the details in this stone layer thing here. Essentially, it is a displacement technique which works in texture space and allows for mimicking the higher detail of a surface than it actually is. So every of the tiles you can see here actually are just very flat tiles, but with the help of the parallax mapping, you can see that it actually looks like there would be depth, even though there is not. This effect obviously comes at a cost, and you can, for example, if I select the material here, increase, for example, the quality of the parallax occlusion map steps, so it will now flicker less. If I cramp that up a little. If I push that 2 down, you can see that everything starts flickering a little. This is due to some temporal sampling I use to actually smooth the surface out over time. But if you keep that values reasonable, you should get a good trade-off between performance and quality. So you can also play a little with that slider thingy here. You can also see that the shadows from the sunlight work as well. For the parallax map, within the parallax map, that is just screen space shadowing, while the other shading techniques that you can see here, they are a little flickery. This is because I try to mimic the proper penumbra of the size of the light source. The name of this shadow mapping technique is irregular shadow mapping, I would suggest, or maybe hybrid frustum tracing is something that NVIDIA came up with, and I try to essentially replicate what they did in a quite hacky way. So you can see the shadows that this rendering technique produces are pretty much accurate, exact down to the pixel. And I could, for example, zoom in here, and you'll see that there's no shadow mapping texels, no jaggy pixel edges, but it's pretty, well, as perfect as it gets, I would say. Irregular shadow mapping has a few benefits, not just being perfect in the sense of producing pixel accurate shadows, but it also actually allows for transparent shadowing, which we can, for example, see here. These are the Minecraft blocks for red and cyan glass, and they accurately let some light through them. Currently only the back faces are casting the shadows, which is why the inside of the cyan block is not properly shaded. But actually, shadows and transparencies are a very difficult topic, and I don't think there's a perfect way to handle this kind of situation. But even like this, I think it works actually quite well if you try to avoid situations where you put these kind of blocks inside each other. Then this should actually not be too noticeable. It works with an arbitrary amount of layers, so as you can see, also here the red and cyan shadows, they blend in together properly, so it actually really calculates how much light passes through these surfaces and how much actually then reaches the final occluded or not occluded surface. Currently, the only working light source is the sunlight. I also managed to create a point light or a sphere light, but then I rechanged the material system and lighting calculation system, and then I just didn't bother to update every light source I had. as well as constantly changing how the materials work, and also the lighting model. The engine does use I call it PBR-ish shading technique, as it's not 100% physically based. Or actually, the only aspect that is not physically based is the specular highlight distribution. I made up a new set of shading math for this, or I don't know if someone else maybe did that before me, but I don't know. It actually uses signed angular distance fields, because this then actually allows me to quite easily approximate analytically light sources that actually have a size, like, for example, the sunlight. You can see that as the sunlight has actually a size, which causes this umbra and penumbra, it also should then in reflections be visible as that. Then maybe I can say a few things about the material system. The engine itself is a 100, or it's a very deferred styled engine. So if you here go in the camera settings, well, sometimes I experience random drops. I cannot really say where they are from. You can see two tabs here, one for light. Here we essentially store, or I store, the light information for one image sample. You can see that the shadows are flickering over time, and also the presence of the cubes itself. Currently, to mimic transparencies, I use a technique called hashed blending. Essentially, each point on the surface has a chance to occur depending on what its alpha value is. So in one sample, the surface may actually not render. Therefore, in another sample, the benefit of this method is that it supports arbitrary layers of shadowing and stacking transparencies as you like, which also makes it easier to work with transparencies in general. It may not be as accurate or temporally stable. This is something I have to investigate in, as it is using pseudo-random distributions over temporal change. Thus, I probably need to somehow fix the sampling or the hashing of the alpha values of the surfaces. Besides the information for the lighting, as this is a deferred rendering pipeline, I also have a bunch of textures applied to the camera for the geometry buffer. RGBA 8 is for the albedo. Pretty self-explanatory, I think. Then we have position data, IOR data, which is like a specular, fragment normal data, which is the normal data of each fragment, metallic value, and also roughness and emission. Emission currently is empty, as nothing emits. Emission will be important for the sky, though, as the sky shader will be an emission shader of some sort. Speaking about shaders, the idea is that in the next step of development, I plan on actually integrating some kind of node system so that materials can be created arbitrarily in a similar way like in Blender, for example, even though it will not be as advanced probably. And there'll be a difference in the way the shaders actually work, as the node system will allow you to actually directly write to these buffers here. You will be able to arbitrarily override whatever is stored in these buffers, and this will then be the node system, and in this way you can manipulate the rendering process as you please. This engine is built to mimic various effects which usually only ray tracing engines can achieve. Thus, some sort of sampling will be required, but I have a very strict policy for this engine that it should not introduce noise in any step of the rendering process. Therefore, you occasionally could eventually see some ghosting artifacts. For example, if you use depth of field or motion blur, which are both sampled effects, or I like to call them accumulation effects, as we are accumulating samples over time, or samples over, different samples. Currently, only the depth of field works as there's no animation system built in yet. I could show that off, for example, by just cranking up the aperture, and then you can see it starts calculating samples. This is the way it currently works. I can click on the pick icon here and click somewhere, and then it will essentially focus the area I selected. Let's just take this one. And the benefit of this technique is that it is very accurate compared to usual depth of field algorithms being used in real-time engines. Something like this obviously is quite costly, so if you have very huge amounts of blur, then it could potentially not quite look the way you want it to. So if I, for example, go here, say focus on the sword, and crank that up a little, then you'll see these obvious ghosting effects. In this case, you'll just have to need to crank up the sampling a little and wait a little longer, but eventually it will converge to a pretty accurate result. And now, after all the 2000 samples are done, you can see that it works just as someone would expect. And here you can see one of the benefits of using accumulation techniques for rendering the various effects. Like, for example, depth of field behind transparencies is something that is usually quite difficult to properly do in traditional rasterization engines, but it's something that is not really a problem in this kind of scenario here. Obviously, one of the key aspects I'm going to focus on in the future will be performance, as this currently does not perform quite as well as I wanted to. I have quite a few optimizations in mind, starting with the shaders, some of the algorithms, especially the shadowing algorithm is something that can be drastically improved. There's currently of the almost 40 milliseconds, a constant 5 milliseconds are just getting data from OpenGL, doing one part of the algorithm on the CPU, and then pushing the data back to OpenGL. This alone takes 5 milliseconds, and this rendering time can drastically be shortened by doing the algorithm in parallel on the GPU, actually. But this requires getting into compute shaders, and I have no idea how exactly they work. But I would expect something like this to render within maybe 15 milliseconds after all the optimizations I have in mind are implemented. And then it's a question of how to deal with bigger scenes. I plan on implementing some integrated Minecraft functionalities, like, for example, reading the blocks here. They are read from Minecraft directly, and this thing as well. And also the sword. I'm working on a world reader, which kind of works currently, but is not implemented in this project. So yeah, this, I think, is it for the first devlog. Thank you everyone for listening this far, and we'll see next time.